Okay, so I think we can start with another talk by Paolo Pani. We will be talking about how does a black hole microstate ring down. Please, Paolo, feel free to start.
Okay, thank you very much, and thanks the organizers for this kind of invitation. It's a pleasure. So since the conference was supposed to be very effort to start with this joke here, and in fact my talk will be about how to tell a black hole, classical black hole from a black hole microstate from the gravitational wave observations. And in particular, I will focus on this last part here, which is the ring down. So I'll try to explain how black hole microstate ring down. So as you probably know, I'm essentially a gravitational phenomenologist, and I arrived at this topic after studying for many years the gravitational wave signature of what are called exotic compact objects. That typically are phenomenological or toy models. And I started becoming interested in this topic precisely for what Daniel Meyerson said this morning, that black hole microstates and fastballs are, in fact, a nice top-down model that can be studied coherently. And in fact, I will present together with other results, the work that we have been doing with this gentleman here, precisely related with trying to understand the phenomenology of the ring down for microstates and fastballs, so going beyond the toy models. And the main take-home message of my talk is that for black hole microstates, all the phenomenology that has been studied for many years for the compact object survives, but is way more complicated, and the signature are much less clear than a toy model would suggest. But yes, I will arrive there, hopefully. So this is my outline. I will focus on the ring down of compact objects. Daniel this morning and Nayesh did a wonderful job already, so hopefully my task would be easier. And I would spend some time in trying to sort of demystify the difference between ring down, quasi-normal modes, geodesic approximations, and what we can learn from the time and frequency domain analysis of a black hole spectroscopy. Then I'll spend some time of the spectroscopy of horizonless toy models, essentially just to show you in an easy setting, in a controlled setting, how the ring down looks like. And then I'll finally move to my main talk, which is the spectroscopy of black hole microstates. And I will show you how standard features emerge in that scenarios in a much more concrete way. What I won't cover, also because it was already covered in previous talk very well actually, are interesting topics like shadows, the multipolar structure, the tidal deformability, tidal heating, the gravitational wave memory that was not talked about yet, maybe the discussion session. And all of these can be used together with the ring down to test the nature of astrophysical compact object or astrophysical black holes. I won't even touch any formal aspect of microstate geometries. Most of you will be way more expert than I can possibly be. So I will just really take the phenomenology approach and use this geometry for these studies. So let me start very briefly. Nayesh already mentioned this, but black holes are now everywhere. For the oldest of you, probably this was not the case just 10 years ago. Now everyone is talking about black holes, astronomers, science fiction, even theorists. We have many observations across many different mass ranges, LIGO and Virgo black holes in, say, the stellar mass range, supermassive black holes. We have a picture of them. We see them at the center of galaxies. And so far, they were worth 2 Nobel Prizes, and many more will come in the future. So the question is, why do we still want to test it? And of course, with this community, I think I don't need to motivate these studies a bit, but let me give you a slightly different twist as compared to, say, the theorist approach. So one motivation is that maybe there are objects out in the sky that look like more or less black holes. So there might be systems that are more classical black holes than others because of their properties. And therefore, now that we are start collecting observations, it might be that some events are either outliers or anyway do not fit the picture. And this might be the example of some events that LIGO and Virgo have seen that lie in what is called mass gap for astrophysical black holes, and therefore there are some events that do not really fit the standard astrophysical picture. Maybe this will just require more astrophysics, but it's interesting to keep in mind. There is also a problem from the phenomenological point of view to explain supermassive black holes at high redshift. So we don't know how these black holes can grow to that big mass in relatively short time. And so essentially there is no understanding of the feet, of the seeds of these objects. And finally, we know that there is dark matter in the universe, most likely, and some dark matter models, for example, axions or ultralight fields in general, can produce compact objects other than black holes and neutron stars. So there might be other families of black holes in general. Then there is the more theoretical motivation that, of course, we all want to observe some signature of quantum gravity and quantum black holes to try to guide different models, possibly to rule some of them out. And well, this has been discussed already. Let me just stress one important thing. Some of you, well, I mean, when I give talks, many of the people in the audience might not trust, might not believe that we can see quantum corrections in astrophysical systems. Maybe this community is more open to this. But an important point is that if we don't do it now, then maybe we should really abandon this problem. And the reason is that right now, as also we discussed in the previous talk, we have all these new observations coming out from the electromagnetic and from the gravitational wave window that provide new ways to test astrophysical black holes. And in the future, we will improve current observations, but not in fact that much. I mean, we'll maybe improve some orders of magnitude, one or two, a few, but the actual observations are already there. So either we see some hints right now of, say, quantum aspects of black holes, or maybe this will be hopefully also in the future. And in general, what we are looking for is new physics at the horizon scale, either in the form of models like firewalls or local effects, or in general, and this is the topic of this conference, horizonless compact objects which are regular and they do not have an horizon, like in the Fatzbold proposal. Let me just stress, again, from a phenomenological point of view, that this is not only academic, but it's really a very practical problem. Because if we want to quantify with observations if a given object, a given astrophysical source, is a black hole or not, we should actually have something to compare with. So on the one hand, we have the classical black hole prediction, and on the other hand, we should have a model, possibly a consistent model, that give us prediction for observables, and then maybe do what is called a Bayesian model selection. So take hypothesis A, black hole, hypothesis B, say Fatzbold, and understand, compute what is the evidence using data between these two hypotheses. And it goes without saying that any evidence for deviation from classical black holes will shake physics at its grounds, implying either new physics or new matter fields. Anyway, it would be a measure of discovery. As I was saying, I will here focus only on gravitational wave-based tests of classical black holes. And the picture you should have in mind is what Daniel was showing this morning. So a merger of two compact objects, they approach each other, the frequency amplitude increase of the signal, they merge, and eventually there is a remnant that vibrates in a given way. I won't touch any of these effects that Daniel already talked about, and I will focus instead here on the post-merger phase. So the ring down, trying to understand the different effects that might occur. So let me go back for a moment, because I will assume that many of you are not familiar with this topic. So I just want to give you a sort of an overview. It's interesting that for many years, people tried to model the ring down of, say, a compact coalescence, a compact merger, using a superposition of quasi-nova modes. And this plot is taken from one slide by Timo Damour, based on this paper here with Alessandra Bonanno in 2000. what they found in this paper was a nice analytical model for the two-body, for solving the two-body problem in general relativity, which was a major achievement. And what they have is an effective one-body approach for the inspiler and merger phase that then is attached to the ring down that is described as a superposition of quasi-normal modes. And this was the standard law, essentially, that this phase here, the post-merger phase, is a superposition of quasi-normal modes, and therefore measuring somehow the quasi-normal modes of coalescence can provide a conclusive proof for black holes, for event horizons. Well, one first point that one should note is that quasi-normal modes compared to normal modes do not form a complete set. So not all perturbations can be decomposed in a set of quasi-normal modes, which already tells you that there might be something more than just quasi-normal modes in this picture. So against remaining in the standard picture, what one would aim to is to compute, to observe the gravitational signal, and in the ring down, the signal is modeled the superposition of quasi-normal mode, which means complex damped sinusoids. So there is a complex frequency. The real part is the frequency. The imaginary part is related with the damping time, and essentially is related with the energy dissipation through emission of gravitational waves or through absorption at the horizon if there is a black hole. And these many modes are labeled for a Kerr black hole in terms of the azimuthal number, sorry, the quantum number L, the azimuthal number M, and the overtone number N. There is an infinite tower of them. Typically only a few of them contribute to the signal, and they have different amplitudes and phases depending on the initial conditions. So for LIGO Virgo, for few events, there has been a measurement of at least one dominant quasi-normal mode, the fundamental one, which is not very useful because it just gives us the mass and spin of the final remnant, but it can be used to try to see whether those measurements are consistent with what the inspiral predicts. And so far, everything matched very well. On the other end, in the future, with third-generation detectors, so the future of LIGO Virgo, and with the LISA mission in space, we expect to detect order 100,000 events per year in which one can measure quasi-normal mode. So this will really be a phase shift, a phase transition in the field when we'll start really doing black hole spectroscopy. And clearly for a Kerr black hole, the standard picture is that everything depends only on the mass and the spin. Therefore, even the entire quasi-normal spectrum, so all these numbers here, which are infinite, can be mapped only in terms of mass and spin. So there are two numbers, but infinite modes. So in principle, if you start detecting many modes, you can start doing a sort of null hypothesis test of the Kerr metric and see whether you get some deviations here compared to the standard spectrum. And indeed, the standard signatures of deviations from the black hole picture would be that the quasi-normal mode is different, spectrum is different, so there might be mode shifts because, I don't know, extra dissipation channels in your theory, because maybe the theory is not general relativity. The object might not be a Kerr black hole, so it vibrates differently. There might be many reasons. There may be even extra ring down modes, because GR propagates only 2 degrees of freedom. If there are more degrees of freedom, you will have more modes that might be excited with different amplitudes. We don't know unless we have a theory in place. And recently it has been realized that not only different angular modes, so different L and M's are important, but also overtones, so different numbers N. So in the future, we will really do sort of multi-tone, multi-mode spectroscopy. So let me go one step back and try to explain what quasi-normal modes are, because this will be important also for black hole microstate. So in the standard black hole picture, the perturbations of a Kerr black hole can be written in terms of Schrödinger-like equation of this form here. There is an effective potential that in some coordinates look like this one here. And there is a source term that depends on the initial conditions. So whatever perturbs these systems. And the quasi-normal modes can be understood in several different ways. One is that they are the poles of the corresponding Green's function for this problem in the complex plane, so they are complex frequencies. Another way to see them is that they are the eigenvalues associated with this problem, and because of energy dissipation at infinity and the horizon, these eigenvalues are complex, so they are not normal modes. The physical motivated boundary conditions that you should put to have an eigenvalue problem in these systems are that the perturbation is outgoing at infinity, because you don't want the system to be perturbed by any external source, so to speak. And then they have to be ingoing waves at the horizon. So they have this shape here in terms of this coordinate, r star. In this coordinate, the horizon is at minus infinity. This potential has a maximum which roughly corresponds to the photon sphere, and therefore we understand that these boundary conditions with this potential selects a certain number of modes of eigenvalues, which are the quasi-normal modes of the system. Now, an important point that also Nayesh mentioned in the previous talk is that radiation takes infinite coordinate time to go, say, from the photon sphere to the horizon. The horizon here is really at minus infinity. So whatever we see from the ring down of a black hole has nothing to do with the boundary conditions that we set at the horizon, because it takes infinite time for the radiation to be there. This is an important point that we should always keep in mind, because it also means that whatever happens, say, in between the photon sphere and this minus infinity, will have an impact in the signal. Maybe a small impact, but it will have an impact in the system, in the signal. In fact, I totally quote what Nayesh said before, that only, trying to rephrase it, only a classical black hole absorbs everything, and no matter what, if there is no classical black hole, some of the radiation that goes, say, from here to the horizon in the classical picture will go back. It doesn't matter. I mean, in the end, there might be different models. It can be Boltzmann reflectivity, it can be Fatzbo, it can be whatever. The important point is that we can even take it, if you want, as a definition of a classical black hole. A classical black hole absorbs everything, and therefore we should not get anything back. If there is something, it can be matter, because maybe it's collapsing, so it's taking infinite time to collapse and really form an horizon, or it can be fuzziness of space-time, quantum emission, it doesn't matter, something will go back. And for example, the picture that you might have if instead of a black hole you form a spherical symmetric compact star is something like this. This potential is the same. Suppose that the exterior is Schwarzschild, so it's really the same. The boundary condition here is the same. But because there is a regular interior, instead of having an horizon, you will have, for example, a centrifugal barrier. Here is probably the simplest situation to understand. What happens is that part of the radiation goes here to the left and then is reflected. Of course, if it is a centrifugal barrier, everything will be reflected. But if you don't want to model this precisely, you can model in a sort of agnostic way the process by introducing a reflection coefficient, calligraphic R, that tells you roughly the fraction of energy that is reflected by whatever is in place of your classical horizon. So there are two signatures of this. One is that the boundary conditions of your problem change, and the other is that here there is a potential barrier, here there is something that reflects, so there might be trapped modes within this cavity. So what happens to the eigenvalues of this problem? And this is interesting because the black hole quasi-normal modes are in fact what we see in the signal. What happens here? If you compute the quasi-normal modes, what happens is that you have very different frequencies, completely different frequencies, in fact. What I'm showing here is the real versus imaginary part of the quasi-normal modes for the black hole, and these are the various overtones of a Schwarzschild black hole. And what is shown here is a simple model of one of those toy models of exotic compact object we were mentioning before, where when there is a reflective barrier, just an epsilon away the Schwarzschild horizon, and you just compute the quasi-normal modes. It's a simple exercise, and then you might try to take the epsilon to zero limit of this problem, and naively one may expect that you will recover the black hole quasi-normal modes. Of course, don't, and it will be clear in a moment why, or maybe it's already clear to you. But anyway, the fact is that the smaller the epsilon, the more different the quasi-normal mode is compared to the Schwarzschild case. And in fact, the spectrum becomes populated by long-lived modes, was frequency scales like 1 over log epsilon, and the time scale, so the damping time of these modes, scales with some power of log epsilon. In fact, you see this is a logarithmic scale, and the spectrum is really totally different from that of a black hole. Then one may argue, okay, but then am I going to see something totally different in the ring down? And of course, the answer is not. And as you would expect, the smaller the epsilon, the closer is the ring down to that of a black hole. And the reason will become clear in a few slides. But before going there, let me just pause for a moment and discuss something, an extra ingredient that will be useful for the rest of my talk, which is the geodesics analogy to quasi-normal modes and the geodesic approximation. So what has been done since probably this seminal work by Ferrer and Machon in 1985 is to describe in some approximation the quasi-normal modes in terms of geodesics quantity. And here I'm sort of extending the argument to a generic stationary and axisymmetric spacetime. And the idea is the following. If you start with this generic stationary axisymmetric metric, so all these quantities are only function of r and theta, you can compute geodesics. And in particular, there are 3 frequencies which are relevant. The orbital frequencies, so this is the frequency of circular orbit around the equator. This frequency, which is related with oscillation of the equatorial planes, and this is the precessional frequency, which is just the difference between the two. So what has been shown in a series of papers is that if you do a Wkb approximation of the problem here with the Schrödinger-like potential given by this shape here, the quasi-normal modes behave in the following way. So the frequency is given by a combination of these 2 frequencies, omega theta and omega precessional. And this is a Wkb approximation, so it works at high frequency, which here means I, L, and M. Okay. What happens is that when L is equal to M and they are both very large, this combination collapses to omega theta plus omega precessional, and therefore just omega. Okay, so the standard Wkb formula that you will see has a real part, which is just omega, the orbital frequency at the light ring, so at the maximum of the potential. And the imaginary part is given by the Lyapunov coefficient, which gives you the time scale for the instability of this circular orbit. So the photon sphere is where unstable circular orbit exists. So the instability time scale is related with the Lyapunov coefficient. One important point is that all this procedure is totally oblivious to the boundary conditions. There are no boundary conditions here. It's really a local effect that in fact is valid at high frequency. So at very high frequency, I don't care about the details of this potential. I just care about what happens very close to the energy level that I'm probing. And this already shows you that in this regime, at least, it doesn't matter what the object is. If there is a very similar potential, I should get very similar quasi-normal modes according to this picture. An important point is that this is a high L IM expansion. If I take L equal to perturbations, which are the most relevant one for observations, already a scalar field potential or a gravitational field is pretty different. And in fact, for the gravitational perturbations, we have 2 polarizations, so 2 modes, and they are not the same. So axial and polar modes, they differ by parity, and they are not quite the same for a Schwarzschild black hole. So this is just to tell you that the perturbations feel a potential that is universal only in the large L limit, but not in general. Anyway, I will show you that this works very well also for small values of the angular momentum. Before going there, let me also mention that the problem of computing quasi-normal modes is, of course, more involved than just looking locally at this potential here. And this can be understood from the results of this recent paper that was led by a PhD student in Rome here, Elisa Maggio. And what we did in this work was to approximate a horizonless compact object using the black hole membrane paradigm developed by Damour and Thorne. So we, and others actually, we took an exterior that was well approximated by general relativity, so a Schwarzschild black hole, a Schwarzschild metric in the exterior, but instead of the horizon, we replace it by a fictitious viscous fluid. And the reason is that in the membrane paradigm, this can be done also for a black hole, replacing the membrane by a fluid, replacing the horizon by a membrane with shear viscosity given by this quantity here. And this can be shown to reproduce exactly all the dynamics of linear perturbation for a black hole. So what we did was to do the same, but leaving this parameter free. So eta is a free parameter that takes this value only in the black hole limit. And what I'm showing here is the deviation from the black hole quasi-normal modes for the real and the imaginary part. So these are percentage deviations in this two-dimensional parameter space. So epsilon tells me where the surface is of this object. Eta is related with the reflectivity coefficient I was mentioning before. So the black hole limit is when eta is 0, when epsilon is 0, when eta is 1/16 pi. So we are here on the top left. Otherwise, we get a different object. It's important to stress that the potential, the external potential, is exactly the same as that of a black hole. So a geodesics analogy here will give you exactly the same quasi-normal modes of a black hole, but a real computation does not. And in fact, there are deviations up to 20% in the real part, more than 100% in the imaginary part. What I'm showing here in gray is the part not excluded by the first observation of gravitational waves, because as I was mentioning, the mode has been computed for some events at the level of 10%. And therefore, deviations larger than 10% roughly already constrain the model. It's interesting that a part of this diagram is not ruled out yet. However, an increase by a factor 10 in the signal to noise ratio, so essentially future detectors, will constrain this region completely. So I think it would be pretty easy to claim, based on observations, that an object should either be more compact than what is probed here, or the reflectivity should be very close to the black hole, or maybe both. So what happens here in this leftmost part of the diagram that I'm not showing? So for smaller values of epsilon. I didn't mention this yet because the phenomenology is completely different. And in fact, for ultra-compact object that I would define essentially when epsilon is much smaller than this quantity, this should be much smaller in fact, the prompt ring down is identical to that of a black hole, but gravitational wave echoes appears a little time. So Nayesh already discussed a lot gravitational wave echoes, so you already are familiar with this, but let me just give you one slide introduction about the problem. So why is this number? So first of all, epsilon tell us how long does the radiation takes to probe the boundary. And what happens is that if epsilon is much smaller than this quantity, the radiation takes enough time to reach the boundary, longer than what the fundamental quasi-normal modes of the ring down will take to dissipate. What does this mean? It means that if epsilon is much smaller than this quantity, the initial ring down that you will see does not see any boundary condition, so any boundary of your problem. It also means that these oscillations here have nothing to do with the horizon. This is something universal that only occurs because the light ring, so this part of the potential, introduces oscillations in the space-time. So this is an important point to keep in mind. What it has been believed for many years that is a clear signature of horizons, in fact is not. It's just the fact that a photon sphere behaves in the following way. And what the way we found this the first time in this paper was to do a very simplified toy model. Take a wormhole, one of those crazy and unmotivated solutions that we were mentioning before, and study a point particle that falls from the infinity down to the throat of the black hole and emerges on the other side of the universe. And in doing this, it first excites the light ring, and this is the light ring excitations. and then it enters the wormholes and something else happens. So what happens? In a black hole case, nothing else happens. And the reason is that radiation is not reflected back. So what happens is that this is the initial ring down and then the signal dies off. In the wormhole case, something goes back because it's reflected by the potential barrier that is formed in this throat. This is really just a toy model, but is a sort of universal behavior that you will see wherever there is something different other than a classical black hole. As we discussed before, a sort of universal picture is that the echo delay time scales logarithmically with epsilon, and this is very important because it means that if epsilon is super small, still the echo delay time cannot be huge. Is, say, parametrically larger than the dynamical time scale of the black hole, but not, only logarithmically larger. So let me show you better what's going on here. So what if you start perturbing one of these objects, what you will see is this shape of the signal here. So a series of repeated echoes, in fact, of ever decreasing amplitude that depends on the reflectivity of your system. So the delay time depends on epsilon. How much the amplitude decreases depends on the reflectivity. And a simple way to understand this is by looking at this two-dimensional diagram. So this Z is what I called R star before. It's the tortoise coordinate. This T is time. And imagine that there is a merger. So part of the radiation immediately reaches infinity. Part of the radiation crosses the photosphere. It goes in the interior, is reflected. So there is a reflectivity coefficient. It goes back here. Part is transmitted. This TBH is the black hole transmission coefficient of this barrier. Part is reflected, and this RBH is the reflectivity coefficient of a black hole, and then so on and so forth. Each time there is a bounce at the surface, there is a reflectivity coefficient added. So you understand that the structure, this is R squared for the second echo, and so on and so forth. Okay, so how about detectability? I plan to talk about this, but I will skip most of this because Nayesh shortly already gave a very nice overview on the topic. So I think that the summary is that there are contrasting results for the presence of echoes in LIGO data because Nayesh and collaborators did a really great and careful job in looking for this effect. And finally, this has been taken seriously by LIGO and Virgo people. And now there is an ongoing and very interesting debate about that. As Nayesh was mentioning in the latest LIGO and Virgo paper, there was a claim of no statistical evidence for echoes, but the situation is very complicated. What I want to stress are two things, in fact. So one is that to me is quite interesting that we are currently discussing this, and there are actually echo searches pipeline in LIGO and Virgo. They are now routine. So for each signal, LIGO and Virgo people will look for echoes, which is sort of interesting if you think what was the situation a few years ago. And the other point, which is very important, is that, and also Nayesh mentioned this, the waveform modeling here is crucial. The echo signal is very complicated. And well, I mean, if you search for something, of course, the evidence that you will get only depends on what you are searching for. So having very accurate echo models is crucial. And also there is a very simple estimate that I'm showing here. This is the typical constraint that you can put on the reflectivity of the object, depending on the SNR. So this is the signal to noise ratio in the ring down. And LIGO can probe SNR of this order, of order 10, which means that with current sensitivity, one can make a sort of 2 sigma claim for a reflectivity as large as, say, 0.9, 0.99. Actually, this is, 0. A few, essentially. What it means that it would be very hard for LIGO, at least, to probe regions in which the reflectivity is close to 0, it's close to the horizon case. Essentially, what LIGO can probe is only larger reflectivity. In the future, we can do much better, either with more statistics or probing smaller reflectivity. So as I was saying, waveform model is crucial, And there has been a lot of improvement in the model. And let me again cite this nice review by Abeli, Ashordi, and collaborators. And I just here want to show you something before then moving to black hole microstructures, because I think it's interesting to understand how complicated the problem can be even in a toy model. So I'm showing here the results of a template that we developed in this series of papers, not because it's the best, but just because I can show you how complicated the system is, even in this simplified approach. So the template depends on the spin of the remnant, chi is the spin, on the reflectivity, and this calligraphic R is the reflectivity. So if you start with 0 spin and reflectivity equal 1, the situation is simple. You see echoes, and these two curves are the two polarization of gravitational waves. We start with something that is linearly polarized, it remains linearly polarized, the amplitude goes down a bit, and the echoes are repeated. This is roughly what LIGO uses right now in the searches. But then if you start putting the spin, because of mixing of polarizations, you start with something that is linearly polarized, and you end up with echoes in both polarizations, and the shape changes because there is mixing between them. Not only, if the reflectivity is not unity, suppose that is a complex number, it can be complex, of course, it's just a coefficient, and this is just a phase, so it means that overall the absolute value of this is still unity. What you see is a very peculiar structure. For example, you might have 1, 2 echoes, and then there is no echo here. There are again echoes in one of the polarizations, and this is related with the specific form of the phase. Not only, if the reflectivity is smaller than unity, here using 0.5, you see that the amplitude of subsequent echoes is much more suppressed. And this is, of course, because each echo is suppressed by a factor R compared to the others. So the take-home message is that everything is very complicated. If the reflectivity is small, these echoes are small. And it's true that the delay time is universal, but the amplitude is not. So this is really model dependent. And this is still a toy model, okay? So let me now move to microstate spectroscopy. So what we tried to do in this paper was, okay, we had all these expectations for exotic compact objects. How about microstate geometries? Because in that case, we have a nice consistent solution, actually a huge class of solutions to some supergravity theory, and we want to study their ring down. So what we did as a first step, just because it's the simplest thing one can do, is to study the evolution of a test scalar field. So we just solved the Klein-Gordon equation on this microstate geometry as a proxy to the real perturbation of the system. Of course, the problem is very simplified in this case, but it's already very complicated from a computational point of view. And the reason is that these geometries do not have any spatial isometry. So a Kerr black hole is axisymmetric, it's equatorial symmetric, so it's much simpler. And we can even separate the problem. In fact, there is the so-called Teukolsky equation, and eventually the ring down is understood in terms of a single ordinary differential equations. Here, we don't have symmetries in general for microstates, and we have to do a 3+1 evolution of the Klein-Gordon equation. There is no shortcut. What we considered is these solutions here described in this paper and in others. So it's a 4-dimensional, so with the 4-dimensional reduction of the 5-dimensional geometry. This is the ansatz in 4D, and is written in terms of some potential that has some poles at the centers of these charges. And in fact, a nice way a pictorial way to describe the solutions is by looking at where the centers are. The black hole is where all the centers collapse at one single point, and this is a spherical symmetric charge black hole, supersymmetric Grayson-Osson solution. And then we consider different cases. Here, I will focus on axisymmetric, axisymmetric solutions where the charges are along the z-axis, or what we call scaling solution where the charges are on equilateral triangles. Let me just stress that, however, this is just to pick some solutions. Our method works for any stationary geometry. So the only assumption here is stationarity, and there is no assumption on particular symmetries of the background. It's interesting, as we were mentioning before, that there is by construction no ergo region in these solutions, which is interesting because, well, we can discuss it later, but there is a very well-known ergo region instability for horizonless compact objects. So whenever they are horizonless and they have an ergo region, they should be unstable on some long time scale. But here there is no ergo region here, so we were not expecting any instability. Okay, so let me show you some results, and these were done by very sophisticated simulations by Taishi Keda, who's postdoc here in Rome. So what I'm showing here are different time snapshots, t equals 0, 15, 30, 45, and 60 m. First row is the black hole case. And what we are starting with is a spherical symmetric sort of Gaussian pulse with some shape. So we start with this spherical shape and let it evolve. In a black hole, the black hole is spherical symmetric. The initial pulse is spherical symmetric. So what happens is just everything remains spherical, and you see that the black hole rings down in the way you would expect. At say 15, 20 m, there is the main burst of radiation, and then everything dies off because the potential, the signal is just an exponentially down sinusoid, it's ring down. What happens in the Fatball case, and this is for the axisymmetric solution, this one is for the scaling solution, you see two qualitative features. We are starting with the same initial data. The first feature is that, of course, as you can see, now the spherical shape is lost, and the reason is that the background is already non-spherical, so you already get some deformation of the initial spherical wave packet. And not only that, if you look at, say, late times, say 60 m, compared to the black hole case, there is still some radiation going on. And in fact, there is some radiation that is repeating itself. Now, let me show you better what's going on by playing this movie for you. This is taken from our beautiful webpage. And here we have the two examples, the axisymmetry and the scaling solution. I will play the first, but it's very similar to the other. So let me, before I start, so what you will see now is a slice, a spatial slice in the X and Z component of the signal, and you'll see on the top that as the time passes by, what happens. And this is what happens. So you see that initially the shape is already non-spherical, and then you start seeing that there is a repeated radiation. Sometimes you have a dipolar structure, and there is something here, and then there is a quadrupolar. So the situation is very complicated, but it's clear that there is radiation going on and out and on, in and out this radiation. And you see this is 1000 m, and you still get some structure. So it's completely different from the case of a black hole. And doing the simulation, well, Taishi can certify this, is very challenging because you have to evolve 3+1 partial differential equation for a very long time. So more quantitatively, what happens? So this is essentially a snapshot taken from those movies, and I'm showing here the field as a function essentially of the time at a given extraction radius. So in this case here, I'm showing the black hole, the black hole signal. And you'll see that there is a standard ring down, then there is the power low tail, that is also a standard feature of black holes, and this signal is very well fitted by quasi-normal modes of the black hole. For the Fatball, well, the situation is much more complicated. There are two main effects. So the first one is that you see that there are some repeated signals. The second one is that there is a long-lived tail that is related with the long-lived quasi-normal modes of the Fatball as compared to this decay here, which is much faster and is related with the black hole one. An important point here, again, this is L equals 0, this is L equal 2. Sorry, this is L equal 2 for the black hole, this is L equal 1, it doesn't matter. the important point is that we always started with a spherical perturbation. So the fact that you see L equal 2 here is due to mode mixing, which complicates the picture a lot. So imagine that you have a geometry of this shape, so the multipolar structure is deformed, and radiation can be reflected in very complicated ways. So this is why the signal is so much complicated as compared to even to a toy model.
Paolo, can you
Paolo,
just
you spoke in 45 minutes, more or less. Huh?
Okay, I'm almost done. Thanks.
But can I just ask, the initial data you're using, you're putting a Gaussian pulse or Gaussian lump inside the light ring of the black hole and then letting it go, or where are you putting the initial scalar field?
So we did many different tries. For these simulations is a Gaussian, it's almost a Gaussian, but anyway, it's a profile that looks like a Gaussian, centered at the origin, and the three centers are within, say, the main support of the Gaussian, within the light ring. Anyway, yes.
So the Gaussian's pretty much dead once it's outside the light ring.
Yes, exactly.
Got it.
Yes.
Okay.
We did also different configuration, but for this particular simulation, this is the case. Okay. Yeah, so something that might be trivial, but I think is still interesting. This is also the first, I think, as far as I know, sort of numerical proof that microstates are dynamically stable, because if they were unstable, for example, if they were an algorithm instability, we will see this signal growing in time. We were not expecting them to be unstable, of course, but it's nice to see them in simulations. Yeah, so I think I have just 2 slides.
Sorry, can I ask a question here?
Sure.
Sorry, Paolo, for interruption. So these have 0 temperatures. These, I guess you said there is no there's no ergo region and there's no temperature. So there's no Hawking radiation you expect from this, right?
Right. So this is so these are microstates of an extremal Razor Nostrum black hole. Yes. As Daniel was mentioning this morning, they also have non-supersymmetric solutions, which also have no ergo region. So in that case, there is no ergo region as well. In principle, we could do the same kind of study for new solutions.
Okay, thank you.
Sure. Yeah, one important point I mentioned before, the geodesics analogy, and building on this paper here, we were applying this geodesic analogy also to the fastball case. And to the black hole case as well. It's interesting. So what I'm showing here are the results from extracting the modes from this evolution, or computing them when possible with frequency domain numerical codes, or doing just the geodesic analogy, which gives you this nice simple formula. Beta is the charge, is the ratio between 2 charges of the 4-charge black hole. And what we see, very briefly, is that the geodesic analogy works very well even when L is equal to 1. Actually, even when L is equal to 0, it works remarkably well, which is interesting. Also, it simplifies the problem a lot. Of course, what this is capturing is not this behavior here, it's just the initial prompt ring down, so to speak, the same that a black hole would have. And in fact, based on this analogy, we can also do something more quantitative. For example, take different solutions and compute the black hole quasi-normal modes in the geodesics analogy, which agree within few percent with exact numerical computations, and then do the same for fastballs. And what you see here is that L is essentially is a measure of the distance between centers. So the black hole limit is when L goes to 0. And you see when L is very small, the fastball quasi-normal modes are very well approximated by the black holes one. And the difference will become smaller and smaller. So what this tells you is that the prompt ring down is approaching the one of a black hole, as expected, in fact. But this is a consistent model. There is no like ad hoc surface or nothing. It's really what you will see. On the other end, this delta T is the echo delay time that Francisco Morales was asking before in the previous talk. So is computing the geodesics, the time that takes radiation to go from, say, the light ring to the interior of the geometry and going back. And as you can see, the smaller the L, the longer the time scale, and this gives you the echo delay time. So the appearance of this features is governed by this quantity here. So by how long does the radiation takes to probe the geometry. Finally, one means to speak about an important numerical issue. As you know, four-dimensional microstates are singular at the centers. It's a fake singularity because the 5D geometry is regular, but numerically this is an issue. In order to fix this, what we did was to regularize with an error function governed by this parameter epsilon and try to take the epsilon equal to 0 limit. What I'm showing here is how the results sort of converges the smaller the epsilon you take. So there seems to be a convergence when epsilon is small. And this is a plot that is in the paper without this black line here. I'm adding this because this is a much smaller cutoff and shows you that in some cases there is convergence for very small epsilon. An important point, however, is that the smaller the cutoff, the more difficult it is to reach numerical convergence. Means that we need more numerical resolution, and at some point the problem becomes intractable numerically. So this is something to keep in mind, that the price to pay for this regularization is having more, requiring more resolution. On the other hand, there are ways to go around this. For example, computing the boundary conditions from 5D and then implement them in 4D. Numerically, it might be tough, but we have some idea how to do this. Or just do the simulations completely in 5D. It might be an option, but it will require a different study. Anyway, this is something to keep in mind. So my conclusion, we are really leaving the black hole era. There are plenty of discovery opportunity for new physics. As also Daniel was saying, I totally agree with him. Black hole microscape phenomenology is now in full blossom. There is plenty of room for exciting results. I think an important point something that is emerging from many different studies, that the phenomenology of black hole is way more complex or messy than what a toy model would suggest. This is something to keep in mind, just because the solution is very complicated. Observation give us strong evidence for light ring, for example, the Event Horizon Telescope observations, and also the radiation waves. But probing an horizon is something different, and probing the quantum structure is something much more involved, and we are not quite there yet. Maybe we will never be there, but it's worth, I think, looking and trying to constrain these models. I would like to conclude with 3 points that maybe will be discussed in the discussion session. I was focusing on SUSY solutions, and of course their chart. Going beyond this would be interesting. It might not actually not be an issue, because having extra fields is not something that worries me that much, coming from modified gravity when there are unmotivated scalar fields, vector fields, etc. It would be very nice and important doing dynamical simulations. Our study was one of the first trying really to sort of port numerical relativity into the game, but the final goal will really be, for example, forming a microstate dynamically and see whether it forms or whether the simulation, the outcome of, say, a collapse is a classical black hole in this theory. And then there is some of you know that I'm obsessed by this problem, the measurement problem. That is something that I really would like to discuss more in the discussion session, which is related with the fact that here we were just looking at a single specific microstate geometry. If I do a measurement, am I seeing this particular atypical state, or am I seeing an averaging of many microstate geometries that will maybe the quantum superposition will wash out any signal, makes everything very even more complicated than what I was showing here. So this is, of course, an important limitation that we should clearly clarify before really confronting FATWA with observations. Okay, I think I'm done. Thanks for the attention, and if there are any questions, I'll be happy to discuss.
Thank you very much. Thanks. Yeah, any questions? So there is one hand up. Yeah, please go ahead.
I think that's you, Stan.
Sorry. We cannot hear you, Stan. I'm sorry.
Yeah, I think Stan was first, or
Yes.
I didn't see exactly. So maybe you can go ahead, please.
Go ahead. I'm sorry.
Stan, your audio is terrible. Can't hear you.
I can't fix that because my computer's coming. Can you hear me?
It's a bit choppy.
Maybe put your question in the chat.
Yes, indeed.
Maybe I have a quick question, which maybe I can ask first.
Okay, maybe Nick, go ahead. Yeah.
Just a quick question. When you talked about the prompt, you talked about this, the microstate geometries exhibiting some kind of prompt decay in the quasi-normal mode. Is that just simply the mode falling down the throat before it even turns around and comes back again? Is that what you meant by prompt decay?
Right, yes. So if the picture I have in mind is that far away, say from the cap, the potential will be something like, simplified version of this potential here. So whatever perturbation happens, it will excite will perturb the space-time around here, the light ring, and this is what you see, even before reaching, the interior and be reflected back. So that is universal in that sense.
Right. I have a comment, but I should let Stan have a go now.
Hello, can you hear me better?
A tad.
Gosh. So let me try, and then I'm writing in the chat anyway. So
I think we can hear you now. If you try to pause your questions.
Yes, I was struck by the values at the table that Paolo showed between the quasi-normal modes and the fuzzball frequencies. Yes, how close they were, and I was just wondering, is this coincidence, or does it mean that in practice it's not possible to distinguish whether we have a fuzzball or we've got a black hole quasi-normal? Okay, so these are very good questions. Maybe I was a bit fast here. So the way I see this is the following: if L is very small, and we have reasons to believe this L is small. This L is similar to the lambda that Daniel was showing before for the fuzzball, for the shadows. If L is small, the fact that these numbers are very similar means that the prompt ring down would be the same. So right after the merger, what we will see is the standard prompt ring down of a black hole, this part here. Nothing will change, just because what I was mentioning before. Small L means that the throat is very deep, and initially we don't see the tip of the throat, we just see the excitation of the light ring. What I'm more worried about from this table is this number here that can become pretty large when L is small. So, and here again, it becomes a matter of numerology and parameter space. Suppose that L is not 10 to minus 4, it's 10 to minus 20 maybe, which is still, if you think that L is Planck scale is still a reasonable number, it means that this delay time can be huge. And if it is huge, it means that the first echo appears much later in time. And of course, it would be totally deformed, or maybe there will be chaotic orbits like what we discussed before. And it would be much harder to see them. So to me, the main limitation is that the echoes can be either delayed in time very much, or their amplitude is smaller than what expected, just because the effective reflectivity is small, or because the radiation is effectively trapped within the object. So it's true on the one hand that there will always be something, but maybe that something will be either postponing time very much, or to an amplitude which is too small to be detected. But I was still struck by the fact that this table seems to indicate that in practice, it seems very hard, almost impossible, to distinguish whether you've got a fuzzball or whether you've got a black hole, a black hole microstate, because quantitatively, the frequencies seem to be the same. Yes, but these are only the prompt ring down. So even if these numbers were exactly the same, and they would be if the photon sphere were exactly the same as that of a black hole, you will still see echoes at late times. So that is what I argue the fundamental smoking gun for something else beyond the horizon. The problem is at which level the amplitude of the echoes is excited.
The other possibility, Paolo, is that L is not so small.
Or L is not so small, yes. Yeah, if L is not so small, it means say 10 to minus 2, then we get deviation at the level of 1–2%, which is within reach future observation. In that case, yes, definitely.
More questions?
So I just want to make a comment that the thing about zero temperature here is important because I mean the classic the original type of echoes that I mean you describe in terms of epsilon description, like m times log epsilon. Epsilon for in the zero temperature limit in fact goes to infinity, or sorry, goes to zero, I should say. So so these are kind of so if you do have a finite temperature, that logarithmic term will show up. And sorry, let me take that. It's not the epsilon, it's 1 over temperature. The echo time goes as 1 over temperature times log of epsilon. And if the temperature does go to 0, then that becomes infinite. And these are kind of beyond the kind of higher order corrections that you're finding in that sense. But if you have a finite temperature, which we expect for all astrophysical black holes, then that time would always be basically 1 over temperature times some logarithmic factor. So in that sense, I'm saying that maybe we shouldn't worry about this because this is a zero temperature and you don't expect that logarithmic dependence for zero temperature. You only expect it for finite temperature horizons.
Yes. So if I can, I agree with this comment. On the other hand, I'm also worried about, so suppose that the temperature is finite, but then because of the very deformed geometry, radiation, instead of going on a straight line and taking, say, log of epsilon, it starts to bounces back within the centers, and therefore it comes out on a much longer time scale, even just because of geodesic motion.
I mean, I think that is a concern. Sorry, go ahead.
I think it's important to clarify the discussion about echoing off of what. The point is that what Paolo's talking about is echoing off the bottom of a microstate geometry, and what you're talking about is perhaps some stimulated emission from a cloud of a plasma around the horizon. I think echoes can come from many sources, and the zero temperature case with the microstate geometry is a big geometry that's just turning stuff around, which I think is intrinsically a different scattering process than the one you're talking about.
I think I want to disagree with that. I mean, I gave the plasma as an example because that's kind of the tip of the iceberg where you can when you can do calculations in a more controlled way. But I don't really think there's a distinction between microstate geometry and plasma. Just plasma is just kind of the tip of the iceberg, but the whole the entire thing is the.
But you said it yourself, at zero temperature in your formulation, there is no echo, it's infinite return time. But in everything Paolo is talking about, there is a controlled return time set by the conformal field, theory. So whatever it is, there are different things that are being bounced off of.
Can I comment, can I add something
Fair,
on this point? Okay, I think that for quasi-normal modes, the temperature is not the important problem. It's the photon sphere. It's not the horizon. These quasi-normal modes are produced at the photon sphere, not at the horizon. Therefore, when the temperature goes to 0, we already see that the bound of Maldacen and so on is violated, because what is important is the photon sphere in that case. There is a very small region when the black hole is near to extreme, where the temperature, for this bound that is 2 pi t, is violated. This is valid just for large.
No, that's a good point. I think it's fair. There are really two different scales, and I think temperature is one, and then here L is another one. I guess, yeah, I agree. They're both. I think that they both can be important. Yeah.
There's another comment which I'd like to make. So all these calculations are assuming that the microstate geometry is frozen, and you are scattering something off it. But we know very well that, for superstrata and for all the other geometries, there's a huge modularized space, and especially for supersymmetric black holes, but also for non-supersymmetric, we expect to have a huge number of nearby configurations. So when you throw something into the microstate geometry, the microstate geometry itself will be bounced into some nearby states, and there'll be a very messy process. And the question is, how much can we trust the result that, in a frozen microstate geometry, you get some echo. Maybe when you have a more complicated, microstate in a moduli space, maybe if you throw something in, it will just excite other modes, and the information will just be lost. So that's and nothing will come out. That's one.
Yeah, maybe just one comment about this, but maybe this is more for the discussion session because I'm really interested in this problem. Of course, I agree with you, but then I guess my worry is, suppose that we believe the picture is what you said, then it looks to me that we should not even look for phenomenology, because either for echoes or for the shadows that we mentioned before, if it happens that any kind of radiation, electromagnetic gravitational waves, is absorbed by one of these states in order to produce another, which is very close in parameter space, then it's just a black hole. I mean, for the observation point of view, this is a killer.
I'm not sure I agree with that statement. I just want to make a further remark based on a calculation that Emil and I made last year, which is that basically you find that the echoes, if you allow the string to excite, don't actually come back. But what actually happens is that, and I think it plays to this point that you were making earlier, that it's very hard to do microstate geometries. I think a microstate geometry will have some kind of effective viscosity, in the sense of you drop a particle in it, and the transfer of energy to the stringing excitations, or the transfer of the energy to the background, as Joseph was talking about, might be computable as some kind of effective viscosity that you could put into your numerical simulation. I think that might be the way to bridge the gulf between what you're doing and what we're doing, which is to try and use the details that we understand of microstate geometries to calculate effective hydrodynamic properties on probes. And then you can put them into your numerical simulations and perhaps see similarities and differences. That's why I like this sort of plot that you were showing about effective viscosities and black hole viscosities. I think that might be a place where we can try and connect the dots.
Yeah, it's not only the
okay, so
problem. I mean,
yeah, maybe we can continue this the discussion, right? Maybe if there are more questions on directly on the talk. So, okay, I had one very naive. So in this table, I think you showing that you can calculate the return time delta t, right, from first principle in this example of supersymmetric fastball. Can you also calculate the reflection, right? So the other parameter that you were talking about.
So the short answer is yes, and the reflectivity here is unity, right? Is related with also what Daniel was saying in the morning. Everything that goes in eventually goes out here. There is no horizon. So it can be trapped there for a very long time, but eventually it has to go out. In practice, it's much more complicated because there is mode mixing. So it's not that we throw, say, an L = 2 mode with unity energy, and then we wait and we see that it goes back with some other energy. We could do the reflectivity because everything will be mixed. So it's very hard to map the toy model with a reflectivity coefficient and an epsilon to a specific fastball model. But in this specific model, there is no absorption at all. There is no viscosity. So strictly speaking, the reflectivity is unity.
Okay, yeah, thanks. Any more questions?
Actually, on that point, this is interesting because even if the true reflectivity is 1, but you get at a lot of modes at high L's, for example, then effectively you don't see them, maybe because maybe it's harder to see high L's. Actually, I'm not quite sure. I mean, it could be that you might get an effective reflectivity which is not 1 on a mode by mode basis. So I don't know if that's something that you could.
Indeed, Nayesh, we did look into that, and for example, focusing on L = 2, looking at the reflectivity coefficient, precisely what you said, you see that it's smaller than unity because there is energy leaking to other modes, and if you don't compute all of them, it may be small, but you miss something.
Is it frequency dependent then?
I think it's frequency dependent, yes.
Okay. Okay, cool.
Okay, so if there are no more questions, maybe we can close the session now, and then